lectures, we'll end up talking about what happens when light ends up going through a material, whereas reflection is what happens whenever light bumps into and bounces off of material. We will see that reflection still can end up having a bit to say with some of this, and we'll talk about total internal reflection a bit later. But we'll begin discussing the concept of refraction, what ends up happening when light ends up coming to an interface. So whenever we end up having a beam of light, remember again from last time we mentioned that light travels effectively in a perfectly straight line. So whenever you have light traveling in a perfectly straight line through one pure medium and comes in contact with something, of course one thing that could happen, it might be absorbed, we're not going to worry much about that. It could be reflected, we talked about that in the last one. The other thing that can happen is light can pass through. So if that happens, then what's occurring at the interface is that the electric field is bouncing back and forth. So the electric field, whenever the light ends up coming in, the electric field excites the electrons that are on the surface. So then the bouncing of the electric field on one side induces a bouncing on the back side the same way, because it's, and then that's the thing that ends up continuing to transmit through the other medium. And the rate at which it bounces is the frequency. And so the frequency is the quantity that stays the same going from one side to the other. What will not be the same is the speed, because of the interaction between the light and the electric charges around it. And so what will then happen is, as it changes the speed, the angle of transmission will change. It will still be a straight line, as long as it's a pure material, and isotropic. But if you've got pure isotropic material, one side it comes in here, the other side it goes at some other angle. And Snell's law is the way to be able to describe the relationship between the two. So each pure material is going to end up having a quantity called the refractive index, which we mentioned in the last video. And the refractive index of the material is the ratio of the speed of light in vacuum to the speed of light in the other medium. And that number is always going to be greater than or equal to 1. It's only equal to 1 if it is vacuum. Otherwise, it's going to be possibly very, very slightly more than 1, but it will always be more than 1. And the other thing about this quantity is it will depend on what the frequency actually is. It depends on how fast the electrons have to bounce. That will end up affecting how it responds to the charges that are built around it, which is the reason why the electric field, why the refractive index is different from 1. Snell's law, you could end up reasoning out from looking at the components of your electric field. It's the electric field component that's horizontal. So if you end up thinking about your angle of transmission, that the cosine of the angle would be the part that's going this way. The sine is the part that's going this way. So the oscillation this way on the top, the refractive index times the sine, will equal the refractive index times the sine on the bottom side. So that ends up being Snell's law. Refractive index, it relates to other things we've talked about. The speed of light is 1 over, in vacuum, is 1 over the square root of epsilon 0 mu 0. In another medium, we can end up having other quantities that are medium specific and frequency specific. The epsilon inside of a material will end up being your dielectric constant times epsilon 0. We talked about, we didn't call it epsilon before we introduced the dielectric constant when we did capacitors. There's also the magnetic susceptibility, the chi, which we didn't worry a lot about with whenever we talked about magnets because we didn't have time to. But that also ends up causing the effective value for magnetism to be different and higher than it would have been in the absence of it. And so that number is also always greater than or equal to 1. And actually, in my notes, I screwed that up. It should not be 1 over the square root of kappa chi. The 1 over shouldn't be there. The refractive index is the square root of kappa chi. So fix your notes on that. I apologize for that. Your dielectric constant, your magnetic susceptibility, and your refractive index all are greater than or equal to 1, and all of them are only equal to 1 in vacuum. Right. Whenever we talk, if we give just one number for refractive index, we said it depends on frequency. That one particular type of light that's very easy to produce and very bright, so it's easy to get pretty nearly monochromatic and really bright, so you're not getting it mixed with other stuff, is the yellow light that's produced in sodium vapor, called the sodium D light. In vacuum, that has a wavelength of 590 nanometers. It's called sodium D light. So whenever we end up, and you look up, if you just get one number for refractive index, that's the number that they're always going to be talking about. It's just practical to end up doing it there. But again, the value of your refractive index, as the frequency changes, when the frequency increases, your refractive index decreases. So for example, in water, for very low frequency, the refractive index of water is not quite 10, but close. For sodium D, which is much higher frequency, it's about 4/3. So just giving you sort of a sense of some of those numbers. One of the things that is a corollary to Snell's law, sine is an increasing function. So if you multiply two things together and they're equal to another pair of things, if one of them goes up, the other has to go down. So if the refractive index increases, your angle of in that medium will decrease. So if the refractive index increases, it will bend in. Your angles are measured relative to the normal to the surface, similar to what we did with a mirror, except it's on both sides. You think about it as being normal to the surface. On one side is the angle relative to that. On this side, it'd be the angle relative to the same normal on the other side when we're talking about transmission, for angles of transmission. Gave a list of refractive indices in there. Vacuum's 1, dry air under standard temperature and pressure, because it is pressure dependent, it's temperature dependent, but it's very, very close to 1 in air. So in general, in calculations, we're not going to worry about the difference between 1 and 1.0005, and we're just going to end up calling it 1. In very, very high density materials, that gases, it could be different, but for normal pressures, for basically any gas, you can end up pretty much assuming that it's going to end up being so close to 1 that it doesn't make a lot of difference. There still is a little bit of difference in certain situations. We might end up starting next week, we talk about nuclear reactions. I might mention a bit about what Cherenkov radiation is, but otherwise we're going to effectively assume that air is almost perfectly like a vacuum as far as light is concerned. I mentioned water is very close to 4/3 for sodium D light. It's an easy number to remember. Quartz is fused quartz is basically glass, so if you talk about glass pane, that gives you a typical number for that. I also gave you for alumina and for diamond. There are a whole bunch of gemstones that are alumina with a little bit of other crap in it, so that a ruby is aluminum oxide with a little chromium, for example, and emerald is with let's see, I think it's with manganese, but anyway, that there's a whole pot full of them that are aluminum oxide and a little bit of other stuff that's mixed throughout. So all those sets of gemstones are like that. And diamond has an exceptionally high refractive index of 2.54. So that there aren't very many things that you get that are going to be bigger than that. So that gives you sort of the range. It's not huge numbers, but the effects, even though those numbers are not really tremendously different from one, we get a lot of physically significant effects due to those. Then I gave an example there. Suppose you end up having light where it travels at an angle relative to the surface, coming in from air going into a piece of glass that has a refractive index of 1.52, comes in at 22 degrees. I want to find what the angle coming out relative to that is. Now, again, notice in this situation when it bends in, it would bend in from this, so it will bend in to be sharper like that. So you'll expect the number to go up. And I gave you this angle, but notice that this direction, the interface is not the normal. The normal is that way, it's perpendicular. So then to end up finding what your incident angle is, you would end up taking the complement of it. So I showed you how you do that. Then you end up just plugging directly into Snell's law, and you end up getting out your angle. One of the things to be very careful on, though, with computing using Snell's law, it would be, in that case, the arc sine of 1 times the sine of an angle, then divided by 1.52. Be careful with your parentheses. That sine of 60 on the top divided by 1.52 is not the same number as 60 over 1.52 to take the sine, then the arc sine. So it's sometimes not terribly far off, but it's not the same number, and it's one of the things I end up seeing from time to time where students end up doing a math error. So just be careful with that. Get used to end up having to calculate that value. Then I will next look at total internal reflection.